Hi folks, this is Heath. We're starting section 13.3 today. Let me start with just a couple of announcements. Just as a reminder, you have one more web assign that's due Sunday. There will be a practice exam that goes up today. Monday's class will be section 3.4. Section 13.4, I think I said 3.4. Wednesday's class is a review. And then exam 3 goes up on Thursday. And we'll stay up through Friday, but I'm aware that many of you will be traveling on Friday. So if you're traveling on Friday, try to get out of the way on Thursday instead. This section is full of just computational formulas, and some of these formulas are tricky because they involve dividing by the magnitude of a vector, and when you take the magnitude of a vector, you get the square root of some complicated expression. The square root doesn't always simplify nicely. So this is computationally difficult, computational intensive. And so this is not a section that I encourage people to blow off. Spend a little time with this section over the weekend, working through the problems. Try some of the practice problems in WebAssign. Bring questions to office hours on Monday. There's not a lot of hard theory in this section, but there are some difficult formulas. So let's go ahead and get started with them. So suppose we have an object that traveled on some trajectory, and the position of the trajectory is given by this function. The arc length between these two times represents the total distance that the object traveled. Distance may be longer than the distance between the starting point and the ending point. This is not this distance formula, because the trajectory may have taken a lot longer to get from A to B. For example, each of these trajectories have the same starting and ending point, but different arc lengths. If we go directly from A to B, that's just a length of 2. We went from 1, 0 to negative 1, 0. If we go up to 0, 1 and then back down, this side has a length of root 2. This side has a length of root 2. And so the total arc length is 2 root 2. If we go around the arc of a circle, the circumference of the circle is 2 pi r. And we're only going around half the circle, so that's just pi r, which is, since the radius is 1 pi. And if we go up and over and then down, each of these segments has length 1, and the total arc length is 4. Arc length is measuring how far you've traveled, which is relevant to, for example, how much fuel you have used up. But it's not the same as just a distance from the starting point to the end point. And there's an efficient formula for computing the arc length. It is the integral of the speed of the trajectory, which is the magnitude of the velocity. So this is the integral of speed. So let's try this example. We want to find the length of this curve between times 1 and 4. Okay? So the derivative is 8. Derivative cosine is negative sine, so that changes us to a positive 6 sine t. Derivative of sine is cosine. This will still be negative 6 cosine of t. The magnitude of this is the square root of 64 plus 36 sine squared t. Squaring a negative term makes it positive, so this will be plus 36 cosine squared of t. But sine squared plus cosine squared is 1, and so this is a square root of 64 plus 36 times 1, and that's a square root of 100, which is 10. Now, I picked an example where the square root works out very nicely for this example, so that our first example isn't too ugly. Then the arc length is the integral from 1 to 4 of 10, which is 10t, evaluated at 4 and 1, or 40 minus 10, which is 30. Okay? But I think you can see from sort of this step here that if I didn't pick a trajectory where the square root simplified nicely, then this integral might be very hard to work out. And so keep in mind that these examples can build up in difficulty, and the later examples we're going to do together will build up in difficulty. I'm not trying to get away with anything. I just want the first example not to be so bad. Okay? So let's keep going. So that's how we find arc length. Arc length is the integral of speed. Let C be the curve of intersection for this parabolic cylinder. So we have a parabolic cylinder, x squared equals 2y, and then the surface 3z equals xy, and we want to let C be the intersection where these two different surfaces cross each other. So we have these two surfaces that cross each other, and where they cross each other there's a curve, and we want to find the exact length of that curve going from the origin to this point here. Okay, so we need to parameterize this somehow, and the way I would parameterize this is to start. This equation only has two variables. This equation has all three variables. So let's start with this equation. And since y is only to the first power, let's let y equal t. No, actually, let's let x equal t. Then what we have now is t squared is equal to 2y. And so y is going to equal to t squared over 2. And then go over this equation, and this equation is saying that 3z is equal to t times t squared over 2, which is t cubed over 2. And so z will be t cubed over 6. And so the curve that we're looking at, this has a correct relationship between x and y, and then this z gives the correct relationship between all three of these. So my trajectory is t squared over 2, t cubed over 6. And so the derivative of this trajectory will be 1. When I bring down the 2, I just get t. When I bring down to t3, I get the 3 and the 6 cancel, and I get t squared over 2. But the magnitude of this is going to be the square root of 1 plus t squared plus t to the 4th over 4. And this is a little bit tricky, but this factors into 1 plus t squared over 2 times 1 plus t squared over 2. Let's take a moment to check that out. First times first is 1. Outer is t squared over 2, but inner is also t squared over 2. They combine to give me t squared. And then last will be t to the 4th over 4. And so the square root of this will just be 1 plus t squared over 2. And so the arc length will be the integral of 1 plus t squared over 2. Our starting point is at the origin, and we reach the origin at t equals 0. And this is our ending point. The ending point we reach when t is equal to 4. T is equal to 4, then 4 squared over 2 is 8, and 4 cubed over 6 is 64 over 6, which reduces to 32 over 3. So our ending time is 4. We integrate this and we get t plus t cubed over 6 from 0 to 4. And so we get 4 plus 64 over 6 minus 0 plus 0 over 6, which will be 4 plus 32 over 3, which is 44 over 3. All right. So that's how arc length works. It's just calculate the derivative of the trajectory, then take the magnitude of the derivative of the trajectory, and then integrate that function from your starting point to your ending point. Let's move on. We've already talked about the unit tangent vector to a trajectory. Let me draw a picture and sort of talk about how these vectors work. Let's say my trajectory is traveling, say, in the xy plane along this curve. The unit tangent vector at some point is the vector that's tangent to the trajectory in the direction that we're moving and has a length of 1. The unit normal vector points inwards to the trajectory, leans into the curve, and the normal vector is sometimes used to measure centripetal force. You may have noticed this when you're rounding a curve, and especially if you're taking the curve a little too fast, you feel a horizontal force pushing you, a little bit here. That sideways force that you feel is in the direction of the normal vector. The binormal vector is perpendicular to both of these, which means it's coming up out of the curve. But it means that these three vectors collectively look like I, j, and k, but they form like a moving coordinate system that moves with the object along the trajectory. So t is a unit vector, n is a unit vector out to the side, b is a unit vector up. They have the same role as I, j, and k, but they move with the trajectory. For people who program first-person video games, this moving trajectory is the coordinate system in which you want to project your objects so that they can be viewed from a first-person perspective. So this is what these vectors are. The unit normal vector is found by taking the derivative of the tangent vector and taking the magnitude of that. What this means is because the tangent vector represents velocity, the normal vector will always be parallel to the acceleration, but it will be a unit vector. So this is parallel to the velocity, and this one is parallel to acceleration. Okay, since you're turning to the left at the at the moment of this here, your acceleration is towards the left. Your binormal vector is outside the plane, and it's pointing overhead from this point of view. The binormal vector is just a cross product, though, of t cross n. And that's how you get your third perpendicular vector. Cross products are something we've seen a long time ago. This isn't a hard calculation once you get through this calculation. And again, we have to divide by a magnitude of a vector And if that square root doesn't simplify, this might be a messy calculation here. Okay? So let's try an example of this problem here. We want to calculate the vectors t, n, and b for this trajectory at the point 1, 0, 0. Well, we reach this point at time 1, cosine of 0, or time 0. Cosine of 0 is 1, sine of 0 is 0, cosine of 0 is 1, but the natural log of 1 is 0. At this time, the derivative will be derivative cosine is negative sine. Derivative sine is cosine. The derivative natural log of something is 1 over whatever that object is. But then we have to multiply by the derivative of cosine, which is negative sine. And negative sine over cosine is the same thing as negative tangent. So this is negative sine t, cosine of t, and then the negative tangent of t. The magnitude of this is the square root of sine squared of t plus cosine squared of t plus tan squared of t. And sine squared plus cosine squared is 1. And now this is a more obscure trigonometry. What's 1 plus tangent squared? That's the same thing as secant squared. And the square root of secant squared is secant of t, or the absolute value of secant of t. Okay? And so the t vector is r over the magnitude of r. That's r prime over the magnitude of r prime. So that's the vector negative sine of t, cosine of t, negative tangent of t, divided by the magnitude of secant of t. But dividing by secant is the same as multiplying by cosine. Secant is 1 over cosine. And so we get negative sine of t, cosine of t, times the absolute value of cosine of t. Cosine of t times cosine of t is cosine squared of t. And negative tangent of t times cosine of t is just negative sine of t. We can drop the absolute values, by the way, because we know that t is equal to 0 and secant is positive at this point. So I've been putting the absolute value sign up through here, but we can drop the absolute value signs. I've made a mess of that. Let's try this again. Signs, because at t equals 0, the magnitude of cosine of t is positive. All right. So since we know that t is equal to 0, then this is equal to sine of 0 times cosine of 0 is 0. Cosine squared of 0 is 1. Negative sine of 0 is 0. And so that's the unit tangent vector. All right. So now we have to take the derivative of this. T prime of t is derivative negative sine of t cosine of t. We have to use the product rule on this. So we're going to get negative sine of t times the derivative of negative sine of t, or times the derivative of cosine of t, which is negative sine of t again, plus cosine of t times the derivative of negative sine of t, which is derivative of negative sine of t is negative cosine of t. Okay? Derivative of cosine squared of t is 2 cosine of t sine of t. Negative sine of t. The 2 comes down, so it's 2 cosine of t, and the derivative of cosine is negative sine. And the derivative of negative sine of t is negative cosine of t. Now we need the magnitude of that. So this is going to be the square root of sine squared minus cosine squared squared times plus square this. This is going to be 4 cosine squared of t sine squared of t. And then this is going to be plus cosine squared of t. Does this simplify? This is going to be sine to the 4th of t minus 2 sine squared of t cosine squared of t plus cosine to the 4th of t plus 4 cosine squared sine squared t plus cosine squared t. The negative 2 and the plus 4, these two terms combine, and we get sine to the 4th of t plus 2 sine squared cosine squared t plus cosine to the 4th of t plus cosine squared of t. All right. This part here factors. This becomes sine squared of t plus cosine squared of t squared plus cosine squared of t. And sine squared plus cosine squared is equal to 1. And so this becomes square root of 1 plus cosine squared of t. All right. The normal vector is t prime over the magnitude of t prime. So it's this vector here, sine squared minus cosine squared of t negative 2 cosine t sine t negative cosine of t divided by the square root of 1 plus cosine squared t. And again, we know that t is equal to 0. So sine squared of 0 is 0 minus cosine squared of 0. This will be negative 1. This is 2 cosine of 0 sine of 0. That's 0. Negative cosine of 0 is negative 1 again over the square root of 1 plus cosine squared of 0 is square root of 2. And so we get negative 1 over root 2, 0, negative 1 over root 2. Well, now we're at the easy point, though, because the third vector is b, and that's just t cross n. And we have these two vectors already. So this is going to be the vector 0, 1, 0, cross product with negative 1 over root 2, 0, negative 1 over root 2. So the x-coordinate will be negative 1 over root 2 minus 0. The y-coordinate will be 0 minus 0. The z-coordinate will be 0 minus a negative 1 over root 2 would be positive 1 over root 2. And that's the binormal vector. That one's, if you can get through n, the binormal vector is not so bad, but we'd have to do this awful calculation to simplify the square root just to get to n. Like I said at the beginning of this video, this is computationally messy. Spend some time practicing through these computations and remembering your trig identities and all that kind of stuff. But it's just a matter of learning some formulas and cranking them out, okay? All right, let's move on. So the problem set to compute these three vectors. This is t, this is n, this is b. All right. The curvature of the trajectory is related to this normal vector. It measures how sharply we curve here. And if you notice that the formula for the normal vector has a t prime on top, the curvature has the t prime on top also, because they're related to each other. The curvature is related to the normal vector here. It measures how sharply the object is turning at that point, is proportional to the magnitude of the centripetal force on the object. We have two formulas for computing the curvature. Both of them give us the same result, but the formula on the right is often easier to work with because we're not having to compute t prime, which is the magnitude of t prime is what we did here. And that's sometimes a messy calculation. And so this trajectory, this formula only uses the original r. And sometimes that's a little faster. Okay? So both of these formulas work. They both give the same result, but sometimes the one on the right is a little faster. All right? So let's try the example on the next page. This is my vector function. We want to find the curvature function, which again is r prime crossed with r double prime. Take the magnitude of that and divide it by the magnitude of r prime cubed. Okay? So let's do some calculation here. R prime, in this case, is 1 e to the t negative e to the negative t. And r double prime is 0 e to the t positive e to the negative t. All right. So their cross product, r prime cross r double prime, is, let's see what we get. We have 1 e to the t e to the negative t and 0 e to the t e to the negative t. So the x-coordinate, we have e to the t times e to the negative t. That is 1, because you're multiplying e to the t times 1 over e to the t. This is 1 minus 1. Nope, this is a negative here. 1 plus 1, this is just, turns out to be 2. The middle coordinate, the y-coordinate, is 1 times e to the negative t minus 0. That's just e to the negative t. And the z-coordinate is, let's see, we changed the sign on the y-coordinate. So this is negative e to the negative t minus 0. This is 0, 1 times e to the t minus 0. This is e to the t. Okay? And now we have to take some magnitudes. We have to take the magnitude of this cross product on top, and then we have to take the magnitude of r prime on the bottom. So the magnitude of r prime cross r double prime will be the square root of 2 squared plus negative e to the negative t squared plus e to the t squared. And the magnitude of r prime is the square root of 1 squared plus e to the t squared plus negative e to negative t squared. All right, this simplifies to 2 squared is 4. The negative cancels. This negative cancels when we square it, and what we're left here is e to the negative 2t. And this is e to the positive 2t. And then this is the square root of 1 plus e to the 2t plus e to the negative 2t. All right. And we want to raise this to the third power in the formula. So this is going to be square root of 4 plus e to the negative 2t plus e to the 2t. But in the denominator, when you take a square root, which is a 1/2 power, and you cube it, you get a 3/2 power. So this will be 1 plus e to the 2t plus e to negative 2t raised to the 3/2 power. And that's the curvature function. Okay. All right. Last little bit here. Let's go back to our diagram that we had earlier, where we have a trajectory that's moving in space. And let's say we're at this point on the trajectory. The tangent vector comes out in front of the trajectory. The normal vector points inwards, and the binormal vector points straight up out of the plane. Okay? The plane that we call the normal vector through the trajectory is the plane that goes through N and B, goes through the normal and the binormal vectors, but it has T as its normal vector. So this plane here is called the normal plane. Okay? You are crossing through the normal plane at any point on your trajectory. This plane that's called the osculating plane is the plane that goes through the T and the N vectors and has B as its normal vector. If you're driving a car, if this red dot here, where'd my pen go? There you go. If the red dot here is a car, the osculating plane is the parallel to the road surface. It's the surface that you're driving on. So it's flat from your point of view. The normal plane is out to your sides. If you were to open your car door, the car door would be pointing along the normal plane. So it's the plane that goes through you, but it goes through you side to side, not front to back, as you're driving along. And the normal vector, which is the vector that determines the centripetal force, is included in both of these planes. That is, it's not normal to each of these planes. It's actually included in both of these planes. Okay? In the last example we're going to look at today, we want to be able to calculate capital T and capital B, or not capital T and capital D. We want to calculate normal and osculating plane. But that means we're going to need to know what these normal vectors are. And so let's get started. This is going to be a little bit of a workout. Bear with us. Okay? All right. So we want a trajectory who has these parametric equations. Okay? We want to find the equations for the normal and the osculating planes to the trajectory. So the trajectory itself is sine 2t, negative cosine of 2t, 4t. The derivative of this trajectory will be 2 cosine of 2t, negative 2 sine of 2t, and just 4. So our first vector, the tangent vector, is r prime of t divided by the magnitude of r prime of t. So let's talk about the magnitude of r prime of t. That's going to be the square root of, when I square this, I get 4 cosine squared of 2t. When I square this, I get 4 sine squared of 2t. And when I square this, I get 16. And cosine squared plus sine squared, again, give me 1, but this is 4 times 1 plus 16 is the square root of 20. So that's the magnitude here. And so the unit tangent vector will be square root of 20 simplifies to 2 over root 5. Or 2 over root 5, 2 times root 5. So when I divide by the 2's, I just get a square root of 5. I get cosine of 2t over root 5, negative sine of 2t over root 5, and the 4 and the 2 root 5 still leaves me with a 2 on the top, 2 over root 5. Okay? So that's the tangent vector. So now let's look at the normal vector. The normal vector is the derivative of the tangent vector over the magnitude of the tangent vector. So we need the derivative of the tangent vector. The derivative of cosine of 2t over 5 will be negative 2 sine of 2t over root 5. Derivative of negative sine of 2t over root 5 is negative 2 cosine of 2t over root 5. And the derivative of this is 0 because it's just a constant. And so the magnitude of t prime will be the square root of 2 squared is 4, root 5 squared is 5, so 4/5 sine squared of 2t, sine squared of 2t, plus 4/5 cosine squared of 2t, which turns out to be square root of 4/5 times 1, or the square root of 4/5, which turns out to be 2 on top and root 5 on the bottom. And that's nice because it will cancel with the 2's and the root 5's here. And so the normal vector will be negative sine of 2t, and the 2 over the root 5 divided by 2 over root 5 cancels. Negative cosine of 2t, and the 2 over root 5's cancel, and once again 0. All right. So now we need the binormal vector, but that's just the t cross n. So we're taking the cross product of cosine of 2t over root 5, negative sine of 2t over root 5, and 2 over root 5, crossed with negative sine of 2t, negative cosine of 2t, and 0. All right, when we cross these in the x-coordinate, we get 0 plus 2 over root 5 cosine of 2t. 2 over root 5 cosine of 2t. In the y-coordinate, we get 0 minus sine of 2 over root 5 times the sine of 2t. This would normally give me plus, but in the y-coordinate we change the sign. In the z-coordinate, we get negative cosine squared of 2t over root 5 minus sine squared of 2 over t. So that's got to be negative 1 over root 5. So that's your binormal vector. Oh, wow. All right. So then the normal plane uses t as a normal vector. And since these are the coordinates of t, the normal plane will have the form cosine of 2t over root 5 times x minus sine of 2t plus negative sine of 2t over 5 times y minus negative cosine of 2t, or just y plus cosine of 2t, plus 2 over root 5 times z minus 4t equals to 0. Okay? And the binormal, the osculating plane, and I'm out of space here. This is the road surface. This is the one that uses b as a normal vector. We're going to use these coordinates here. So this will be 2 over root 5 cosine of 2t times x minus sine of 2t plus negative root 2 over root 5 sine of 2t times y minus cosine of 2, or y plus cosine of 2t plus negative 1 over root 5 times z minus 4t equals to 0. And that's the equation for the osculating plane. So for any given time, this is going to be a constant times x minus a constant, constant times y minus a constant, constant times z minus a constant. This is, at any given time, this is the equation of a plane, but it's a complicated looking equation for a plane because we've got all these manipulations being done to the t. All right. thanks for watching. Y'all have a fantastic weekend. Bring questions on Monday. All right? Take care.